If you have a homework question, just raise your hand, Brett, and call it. Sorry, Ryan.
63 callbackers. So they call them up and
Dave. 72. Let's go Emily.
44.
Let's go Hannah.
75.
Hunter.
42.
Cigar. 12. Eric. Let's go with that. First thing before we do this, though, this was the only class where we didn't get a chance to talk about the piecewise idea. The piecewise idea really goes quite fast. We just didn't have time last time. So grab this, turn it to this side. It's actually a very simple limit question. The thing to remember about a piecewise function is that, like a lot of functions, all you have is a formula. The purpose of the formula is to be able to compute the xy pairs. With a piecewise function, the key difference is that instead of having one formula for computing all of the xy pairs, they give you two or more formulas. And they also tell you what x values are assigned to which formula. So for example, this piecewise function has three different formulas. The first formula, the only x's you would ever plug into this formula on the top would be an x value that's bigger than 0 and less than 3. Otherwise, you don't use this formula. When you have x values that are, well, actually one x value that's equal to 3, you use this formula. If the x value is larger than 3, you use this formula. Questions about what do we mean by a piecewise function? Okay, so finding the limits is pretty simple on a piecewise function, although always remember the first rule of finding a limit, you have to factor and divide if you can. No factoring and dividing here because these don't have any denominators, but a piecewise functions can, just don't in this case. So, I'm supposed to find the limit as x gets close to 3 from the positive side, which means I'm trying to figure out the y-coordinate of this function f when the x-coordinate is just a little bit more than 3. So I look up here and say, well, I just want to find the y-coordinate when x is more than 3. So we just say it as a class. Do I use the top, middle, or bottom formula? Bottom formula. So you can write it down, or you can just kind of think about it. Let's see, a little more than 3. So that's a little more than 7. The limit, therefore, is exactly 7. Now, limit means what am I getting close to? Questions? Awesome. Same thing. I want to find the limit or the y-coordinate of the function f when the x-coordinate is just a little bit less than 3. So look up here again. If the x value is a little bit less than 3, do I use top, middle, or bottom? Top. Top. So let's see. Put in a 3 minus. Square that, subtract 2. Okay, when you're finding a limit, most of the time it doesn't really matter whether you're a little bit more or a little bit less. You just care what we're getting close to. The exception to that is if you are a little more or a little less than 0. So everybody look over here for a second. 0 plus. One person raise your hand. What's the decimal value that kind of represents 0 plus? Like, how do I write that as a decimal? Nicely done. So that's 0 plus. 0 minus, someone else. Let's go over to Ethan. Right? Not quite, no worries. Think of the number line that helps me. Here's 0. We're looking for the value that's right there, and the one that's right there. 0.999 is actually over here by 1. No worries. Let's go here to Blake. There we go. Oh, 0.999? Actually, 0. Yeah, no worries.
Yeah, sorry.
You're okay.
No.
Like that.
Never mind.
Does that make sense? No worries. It's one of those questions that sometimes until you see, you're like, oh yeah, I knew that. Questions? Everybody good? Okay, here's the key. Look, 1 second, Keston. Hey, over here, it didn't really matter if I was a little more or a little less than 7. Because in both cases, I'm getting very close to 7. But if this occurs, where in one case I'm a little bit more than 0, and the other one I'm a little bit less than 0, that's a problem because one case we have a positive value, one case we have a negative value. In some instances that still won't matter, but if we're dividing, it can make a difference because it can cause the sign to change. So normally I don't worry too much about whether I'm more or less, unless I start seeing things like this happen, then I kind of just slow down and think a little more carefully. Just had a question, sorry.
Okay, so mine's on the last box for 14. So when you have a negative number, the closer it is to 0, that means it's like greater than, so like if you have -2, -1 is greater than -2, right?
Gotcha.
Yeah, so when it's asking about -2 being slightly more positive and then -2 being slightly more negative, how would you like do that based on the functions and make it greater than 2?
Oh, if I'm answering this, I say, okay, -2 with a little bit positive of -2, which means more than -2.
Yeah.
Yeah, so I look up here and say, oh, that's this one.
Okay.
Does that make sense?
Yeah.
When x is more than, is that your question?
Yeah.
Good call.
So, like, with the graphing and stuff, you say for find the actual limit, so like, on number 3, to find that one, you look at this, you look at 1 and 2 usually, right? But there's a formula for exactly x equals 3, so what?
Oh, outstanding. Everybody look at this. Everybody knows the question. Really good. When you're finding a limit, you're never considering what's happening when x is exactly 3. So limit always means what's happening when x is a little more or a little less than 3. So don't fall into their trap of making you want to look here. Because when I'm finding the limit, x isn't 3. It's just a little more, a little less. So actually do exactly the same thing you did on the graphical. I just look at these two. And because these are both 7, this is also 7.
So then for 4 is what you look at.
There you go. For 4, I look up there and say, oh, f of 3 is precisely 2. Perfect. Follow up, go please. Correct.
Why do you look at number 1 and 2?
So the thing to memorize is that whenever you're doing an overall limit,
Oh, left and right.
you always have to look left and right. There you go, you remember. Somebody else. Perfect. Okay, just real quick to make sure it's making sense to you, just do this white sheet and then we'll show you the answers. And do that quick. I was just going to walk around if you have a question. Nice for you to talk to each other. And just do the white one. We'll just kind of read the answers, make sure you don't have any questions about the piecewise stuff. So, no one in my other class like A1 today had any questions from the homework on the piecewise. So I really think if the white sheet makes sense, you'll be just fine with the piecewise. We'll get back. And I would, it doesn't, some people were able to figure out, but quite a few got kind of stuck there, so don't worry.
For 7?
This is the definition. But
Oh, yeah.
Going to 1, 1 is 2. Because if the sign has a line under it, that means it's less than or equal to.
On this one, because like,
Yeah, and yeah, so
Same way.
they aren't the same number, but they both work with this function because 1 divided by 2, so yeah, because it's less than or equal to, and with this number it's less than, with this number it's
this
equal
one
to.
they're asking for full number, you don't have to plug in exactly, it's always more or less. But when they want exact value, you plug in exactly one.
Oh, less than.
Yeah, it's a huge number divided by a little number. Still, I don't know, that one was a little weird because it was 1 and then it plugged in the same way.
Power, that's actually the infinity. So much bigger.
I know, it's like,
Try that one.
Well, I don't like that. I don't like that they give you the
So what I
problem
do
and
here
it goes
is
to
if I
work
want to
and
find
you
the value of the function.
like with this one, don't like that they do that because that's feeling it goes everything.
Right. Doesn't specify how to handle X equals. So thinking is, oh, this definition doesn't tell me.
Approaching 3.
So we say.
So it's like a little less than 3. So approaching it. Oh yes, I did the first one because it's not at 3, it's approaching 3. Okay, now I really need that. Maybe I probably like,
Yeah, it's like you're looking at the number of students. All right, here we go. Okay, just what I want you to do is just say it's a classic answer, and then I'll just kind of list if there's any variations. We'll answer questions if you have them. So just say number 5, please.
4.
Louder.
4.
6.
1.
7.
Does not exist.
Does not exist. Non-existent. 8.
1.
Questions on any of these 4? Perfect. Next one. Number 9.
10.
Number 10.
5.
Number 11.
Does not exist.
Does not exist. Non-existent. Number 12.
7.
We have a question here. Perfect. 13.
3.
14.
3.
15.
3.
16. Undefined. We're going to have a question here. Perfect. Okay, so in this packet, I'll let you do the piecewise ones just kind of on your own. And so when you come back to class next time and it says, are you finished with the packet, make sure you've included those piecewise. Like I said, first period they didn't have any questions on the piecewise, so I think you'll be just fine. So, let's go down this list now a little bit. Back some of these problems. So, number 66. I did it last period, so I won't rewrite it, but I want to make sure you don't have questions about it. So look up, hey, look up. Most of this you know, but you may have forgotten, because it's been a while since you may have done similar things, and that's normal to forget. First rule of finding a limit is always, if I can factor and divide, I have to. If I fail to factor, I am going to fail. So the first thing somebody thought last period was to take a 10 from the numerator and a 5 from the denominator. Does anyone have a question here? And so those divide to make 2. Gets us to here. I'll let you catch up in your notes, so make sure you get it written down. I'm kind of watching everybody's pencils here. Okay, next thing. Look up here. Like, I want to see your eyes on this. Like, look here. I want to see you looking at it. It's important to memorize because it happens all the time in calculus. Whenever you have something minus something, it can always be factored. And the factoring is always easy. You simply take the square root of x to the 4. So just say it together. What is the square root of x to the 4? X squared. Minus the square root of a to the 4th would be a squared. Then you multiply by what's called the conjugate. Conjugate means, you don't need to remember that word. I'll use it so you get kind of familiar, but you never tested on it. It's the same thing with a plus instead of a minus. These are called a conjugate pair. Again, you don't need to memorize that word. But anyway, this is the factored version of this. And that's super helpful because that factor also exists in the denominator. Questions to this point? Please, go ahead.
So if I were to not, if we were to not factor that out, like the top part, could you just do x to the 4th minus x squared and then a to the 4th minus a squared? And like
So the top, say one more time, Scott.
okay, so before we factor out the top and it says, well, we take out the 2 and then could we just do x to the 4th minus a to the 4th and then like divide by the x squared and the a squared?
Oh, I got you. Got what you're saying. Yes. So, hey, listen to Sugana's question. It's a really good question, but you can't do that. Like, it may work once in a while, just out of pure luck, but don't do it. I had you write in your notes a couple of days ago that division is only legal. The top is in factored form, and the bottom is also in factored form, and you are dividing matching factors. So you can't divide these two. The x to the 4th and the x squared are not factors of the numerator and denominator. The factors of the numerator right now are 10 and this whole thing. The word factor means it's something that's being multiplied to create negate the numerator. So right now the numerator has two factors, 10 and this. You can only divide numerator factors with denominator factors. So because there's no matching factor in the denominator, you can't divide. These two are factors, they do divide, but these do not. These don't either. Great question, though. Pretty good? What else, please? Show you in a second. No worries. Other question, Eric?
Why don't you, like on the bottom kind of the fraction, x to minus 8, why don't you separate that one?
Got it. Why don't you factor it out? Okay, awesome question. This can be factored. I simply choose not to factor it because I'm looking for matching factors in numerator and denominator. And this already matches this factor. So that's why I didn't factor it out for you. So these two factors, x squared minus a squared divided by x squared minus a squared, they divide to make 1, leaving me with this much simpler limit problem. Now say your question, sorry, misunderstood.
Where like, it looks like you almost like distributed it, but where the x is going.
Oh, gotcha. So you're okay to here. Okay, once I get to here, okay, nobody talk, it really messes with me. So once I get to here, I have to think, okay, I need to plug in a little more than a and a little less than a. So let's see, if I plug in, you're never plugging in exactly a, but it kind of helps you get started. Plug in exactly a, square that, I'm going to get a squared. A squared added to a squared would be 2a squared. So if this were a little more than a or a little less than a, still going to be really close to 2a squared. That's where the x is. Because I'm trying to figure out what happens when x gets close to a. 2a squared multiplied by 2 is 4a squared. So I'm checking a little more and a little less. Don't forget to check a little more and a little less. Question? Awesome. So that's 66. 41. Okay, 42 and 41 are nearly identical. So we're going to look at 42 instead right now, since I already have it written down. Okay, as x approaches infinity, you can factor if you like. This one doesn't factor. But what I often do is I look to make what I call additive comparisons. Like I want to compare things that are being added. So I look at the numerator and say I've got 3 things here. They're all being added. I just need to kind of figure out if when I add them, they contribute equally, or if one term dominates. Like it's much, much larger than all the others. And what I notice is that x to the 8, as you plug in like values of x that get bigger and bigger and bigger and bigger, it's going to get unbelievably large. Well, x to the 5th actually does something similar, but you need to memorize. A power function x to the 8th is going to grow so much faster than the x to the 5th term that when you're plugging in unbelievably large values, this one will be so much bigger than this one. They're both really big, but it's so much bigger you don't really notice that you're adding the other. So it becomes insignificant in the sense of the limit. So really the x to the 8th is the important value. Compared to 3, 3 doesn't even seem like it's even there. It's so much smaller when you're plugging in numbers that get bigger and bigger and bigger and bigger. So I can rewrite the numerator as just, hey, really this limit question is the same as just putting x to the 8th in the numerator. I do the same kind of logic on the bottom to get this. So anyone have any follow-up questions on how I logically said that this limit question is going to be exactly the same as this limit question? Anybody? Okay, important things to remember. Only compare terms that add. Don't ever compare terms that are multiplying to get rid of one. Okay, you can only do this neglecting idea if it's things that are being added or subtracted. Okay, from here I can do a little bit of mathematical kind of simplification. because the x to the 8th will divide with the x to the 4th because they're both in factored form. Gets me to here. I'm gonna have trouble to this point. Oh, please.
Could you just explain the math real quick?
From here to here. What I'm really doing is this. Great question, Jay. I am writing the factors separately. I simply did it in my head. Okay, so I separate the factors. X to the 4th multiplied by x to the 4th is x to the 8th. So this is the same as this, just written differently. X to the 4th times 5 is 5x to the 4th, just written differently. But these divide to make 1. So 1 times what's remaining is just what's remaining. Does that make sense? Please, Kenneth. Oh, got it. Next step. So you're good to hear. Then you go back to the logic thought of, okay, wait a minute. I'm plugging in a value that just gets bigger and bigger and bigger and bigger. Well, the top's going to just get unbelievably large, but really the bottom's just always 5. So it's kind of like, well, unbelievably large divided by 5 is, I guess, 5 times smaller than unbelievably large, but I would still consider that to be unbelievably large. So that's why it's going to. Does that kind of help?
Yeah.
That's a good question. Please.
Do you need to simplify it to x to the 4th over 5?
Or can you just kind of think about it here?
Yeah.
No, you can think about it.
Okay.
That's fine. All right.
So when x is approaching infinity, you just kind of decide whether it's going to infinity, like when it gets to the x to the 4th. Like,
What?
I'm just confused.
You're okay. Keep talking, Kurt. What you have to do is literally, like, you can't really, I guess you can kind of think of some numbers if you like, but you're not expected to do actual computation. So you can think of, okay, x is getting, this just means x grows forever. Go ahead, please.
So if x is going to infinity or negative infinity, will the answer always be either infinity or negative infinity?
No, the answer will be this, 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 or some number. Whatever, I don't know what the number would be. So there are different possibilities. Here's let me do a counterexample. If I'm looking at this one, I look at the numerator, x is approaching infinity. I notice that I've got 3 things being added, so I can compare them. The x to the 5th term is going to dominate. It will become the largest, the fastest. And so I can pretty much neglect the other 2 that are being added. They won't make any significant contribution to the x to the 5th term. So this limit can be written more simply as this. The denominator dominant term will be the 7x to the 6th. Comfortable there?
Yeah.
Okay. I'm going to simplify that to this. These divide, I end up with 1 over 7x. Are you comfortable with the division? Yes, no, either, no. Think of it this way.
Yep.
Comfortable that this is the same as this?
Yeah.
These divide to make 1. So 1 times that is that. That's where that came from. Question? So now, Paris and everybody else, look, there's a difference here. The 1 doesn't change in the numerator. The bottom just keeps getting bigger and bigger and bigger. So this is the opposite situation. If you have a number divided by unbelievably large number, you have an unbelievably tiny fraction. If you have 1 over 1 trillion, if you have a trillion, that's going to get really, really close to 0. So we're not doing this. So the answer to 41, 0. The answer to 42 is infinity.
Okay.
Does that help a little to see the difference?
Yeah, so then when it's a number, how would you get a, like?
How do you get like one of these, right?
Yeah.
Hold that question, we'll probably run into it in a second.
Okay.
We promise. Anybody else on this? Please.
So if the limit said it was going to negative infinity on 42, would the answer be negative infinity if it's positive?
It depends on the powers that are involved. So when I start out the problem, my logic doesn't really change. If this were negative infinity, to the 8th power is still going to be just really, really big and positive, actually. This will mess with the sign of the number, but it'll still be so much. You have to remember, on a scale, you can think of this being the largest value and this being the smallest. But you can also think of this as being large and this is also being large. And 0 is the smallest. It kind of depends on the context. When I'm looking at a limit, I think of this as large positive infinity, large negative infinity. So if I'm plugging in negative infinity, this still dominates. I don't really care about whether it's big and negative or big and positive. This is so much bigger, whether it's positive or negative, it still dominates. Same thing on the bottom. So that gets me to here. I can still do the reduction to get to here. Now I have to pay attention to the sign. But because it's being raised to the 4th power, if this were negative, that's going to switch it to positive. If this is the 3rd power, that would be negative infinity. Anybody else? Please, Dawson.
So is it like a general rule when the power is the numerator is bigger than the denominator that it will be approaching infinity? And then for the opposite, that it would be going to 0 if the numerator is smaller than the denominator?
You're super close. Everyone hear this. Everybody. You're super close to the idea. But you have to be a little bit careful because they're very clever in how they write questions. So the things to remember are these. If x is approaching infinity, it's a really good idea to compare terms that add. If you're comparing terms that are adding, yes, the highest power term is the dominant term. Don't let them fool you, though. If you're comparing terms that are multiplying, you can't compare them. So it's something different. I can't think of an example at this point, but yeah, so what you're thinking isn't always true. So, but you're on the right path. For comparing terms that add, the highest power really is dominant when x is approaching infinity.
But like when you get later into the solver.
Oh, later into here.
Yeah, like how the numerator is smaller than
Oh,
the
yes,
powers.
for sure. Once I get to this reduced portion, then it's pretty simple. The idea is number over something really, really large, it's approaching 0. If it's, really large number over constant, that's approaching infinity. That's kind of what you meant.
Yeah, so if you can see that like earlier in the problem, you have to continue to write the limits to get credit on the AP.
Gotcha. Okay, with regard to how much you have to write, okay, make sure that if you are writing on the AP test, you include the limit statement, because otherwise it really isn't equal. But on a problem like these on an AP test, even if it's in the written section, you can literally answer without writing anything. They won't require writing. Really?
So you don't write the equal when you're like plugging it in, right? Or is this
Correct,
when you don't?
because it's not really equal once you start plugging it in.
Okay.
But I have to put limit here, I have to say it's equal, I have to say it's equal here, here. After that, I just kind of mentally figured out the rest, so. Please, thank you.
So you will get docked points if you don't have the limit in front of it.
If you write just this, yeah, it's not equal anymore. It's only equal because it's a limit. This formula isn't equal to this formula. It's only equal because x is approaching infinity, and we're finding the limit. They're not the same formula. Does that make sense?
You're just specifying that it's a limit.
Yes, it's only because they're limits that they're equal. If they weren't limits, I can't say they're equal. And even if it were the limit as x approaches 5, I still can't say they're equal. It's only because it's the limit as x approaches infinity. You had a bunch of different questions. Did I miss anybody's question? Awesome. Next thing. 76. Okay, something to memorize. You'll need to get this memorized. It'll show up again and again and again. Okay, it relates to Dawson's question. When we're dealing with power functions, the highest power dominates. But then they start mixing in logarithmic functions and exponential functions. Okay, there's a hierarchy here. Exponential functions grow the fastest. Power functions are in the middle. Logarithmic grow the slowest. They all grow. As you're plugging in x, getting really, 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 really big, the top will get big. And if you let x go forever, the top will grow forever. But the bottom will grow much faster. So you end up with a situation where the top's big, the bottom is so much larger, that you actually have a very small fraction. So the whole thing is approaching 0. But you have to have that fact memorized. Exponential, power, logarithmic. Please.
Wait, what does an exponential function?
So it's really simple to memorize. Exponential functions have a base that the base is a constant. So e to the x, e is the number 2.7-ish, and then the exponent is where the variable is located. So that's an exponential function. Power is the opposite. The base is where the variable is located, and the exponent is a constant.
Oh, good.
Does that help?
Yeah.
So they're just opposites of each other.
Okay.
Exponential grow the fastest, power the middle, logarithmic the slowest. But they all grow. Mary, question?
Yeah, yeah.
Very good. Anybody else?
Wait, so how did you get 0?
So where the 0 comes from is, I note that both top and bottom are growing, but the bottom grows so much faster than the top that I end up with a situation where the bottom is like 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, like unbelievably large. Sorry, the bottom, unbelievably large. The top is big, but compared to the bottom, not even close. So it becomes a fraction that ultimately is getting closer and closer to 0. It never actually gets to 0, but it's getting closer and closer. Please, Suzanne.
Wait, so can you write out what natural log x would look like if you wrote it out? Isn't it log base e?
It just means log base e to the x.
And what would that mean? That means like e to the power of x, or?
It's kind of tough, honestly, to mentally kind of process what's happening. If you want to come talk to me individually, I can show you. For this class, it's a lot more effective just to memorize that it grows, just not very quickly. It's a big question, though. It just takes a long time to kind of make sense of it.
So why is E grow faster?
Same thing. If you want to come talk to me, I can show you. If you try it on a calculator, you'll be amazed like how much faster it grows. It's not even close how much faster it is. But I can show you the image. It just takes a little while. Anybody else? Awesome. So that was 76. While we're here, 72. This relates to what Dawson asked earlier. Okay, I don't want to compare this term to this term because they're being multiplied. I can't compare them and neglect one of them. But I can compare these two because they're just being added. As x approaches infinity, just say it out loud. Which will dominate, the 3x or the negative 2? 3x. As x approaches infinity, which dominates, the 5 or the 6x? 6x. But you can't forget the signs. So I create a new limit problem that looks like this. Uh, 3x multiplied by negative 6x, all divided by 4x squared. This is kind of what I meant, Dawson, when I said be a little cautious about the power thing. But you have the right idea. We just have to just be careful. Questions to here? Then I would combine. These two multiply to make negative 18x squared. This also answers Paris's question that you were asking about Paris. It's the example you were looking for. This is 4x squared. You would have trouble to there. The x squareds can divide to make 1. The 18 and the 4 divide also. That becomes 9 over 2. So this is an example, Paris, that when x is approaching infinity, because the top and bottom grow at relatively the same rate, the whole thing approaches a number. Negative 9/2.
Okay, yeah.
That's what you were looking for as an example, right?
And did you only, additive comparison
Only,
when
go ahead.
it's approaching infinity?
It also works when we're approaching 0 to compare things that are adding, but only 0 and infinity.
Okay.
Yeah. Infinity is the place where we use it the most. 0, it's a little easier because you kind of look at it and say, hey, this just becomes close to 0. But you're right on track. Anybody else? Perfect. That's 72. Look here, this is related to what we've been talking about. Okay, just look at it. Just look at this. X is approaching infinity. Which grows fastest, top or bottom? Just say it. Bottom. The bottom grows faster, the whole thing's going to approach 0. Nathan, please.
So when it's e to a power, that's not the same as like a natural log, right? The e to the power goes faster.
Much faster. Yeah, they're actually inverse functions of each other. So fastest growing is exponential. Second fastest is power function. Slowest growing for our class, logarithmic. So this one's 75. Look at it. Hey, come on, look at it. Which grows faster, top or bottom? Top. That's going to approach infinity.
Could there ever be a situation where it approaches negative infinity?
I hear a voice somewhere. There we go. Okay.
Could there ever be a situation where it approaches negative infinity?
Yeah, all they have to do is put in some, like the x is approaching negative infinity.
It's not in one of the problems.
It's
So
not
I
common,
got
but they can.
Negative infinity for one of them.
They can. You have to be a bit cautious. Things change quite a bit when you're approaching negative infinity. E to a negative large number gets really, 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 really close to 0. You can't find the natural log of a negative value, so that messes things up quite a bit. Kristen.
Some of them I've already asked this, but for 74, it's 0, while 75 is infinity, but they're both approaching infinity. So how do you decide if it's 0 or infinity?
It's comparing the top and the bottom.
Okay.
So if you end up with, as x approaches infinity, the top's going to get big, so is the bottom.
Yes.
It's a matter of which is getting bigger the fastest.
Okay.
So in this situation, the bottom gets much bigger than the top, so the whole thing approaches 0.
Okay.
I've written this in class before. It seems to help some people remember. If the top is big, because x is approaching infinity, but the bottom is much bigger, that approaches 0.
Okay.
If it's the opposite, it approaches infinity. Please.
So you said you can use like additive comparison for if it's approaching 0 too. So is it the same idea there?
Yeah, let's look here.
For that one.
If x gets close to 0, which of these two becomes dominant? The 1 or the negative x? The 1, because x is getting really, 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 really close to 0. So this limit problem can look like this. One, which will dominate here. This is going to get close to 0. Adding 6 is going to get really close to 6. That's going to get really close to 4. That's going to get really close to 3. Hey, this whole thing's getting close to a number. 6 over 12 is 1/2. Question? Okay, I apologize. We got to jump to the homework real fast. Okay, I'm passing you out a packet. The homework is not the entire packet. We'll use this packet for 2 or 3 homework assignments. The homework tonight is only 1 through 17.
Yes.
Homework tonight is 1 through 17.
That makes so much sense. This makes so much sense.
The homework is problems 1 through 17. A little bit's okay, but when it's kind of incessant, I can't. The homework is 1 through 17. The answers are in the back again.
The only tough part would be like 6 blocks, the very last. And I love 6 blocks, but I grew up right in PC. So I want 6 blocks. I love the East Coast.
I think we're just gonna solve the problem.
What's the number you gave him? We do 1 to 17. This is a little bit over that, and then after that, yeah, okay, so that's good. We're all the same for this.
-3 minus
Dude,
So this
the way it works, okay, just clarifying the homework system.
Yeah,
Yeah, you're good. Just unplug during class. You're okay. Hey, for the homework system, the way it works is you've already given me the score for this one as far as being prepared for the discussion. Done with that. When you come back to class on Friday, I'll pass the clipboard. You write down whether you are completed on this one or not. That's the second score for this one. But on Friday, you will also write down, you'll also write down a prepared score for this one. That makes sense?
Yeah.
Cool. All right. Look up. We got to concentrate hard. We got like 7 minutes. Look, it goes pretty fast though. Okay, 1 through 17 are only asking you to do a couple of simple things. It's stuff you've done in other classes, so that will also help it go a little bit quicker. A little bit of review, kind of connecting it to limits. 1 through 17, you're supposed to figure out whether the function they give you has a hole, vertical asymptote, or a jump.
What is a jump?
I'll explain. So you're looking for a whole vertical asymptote or jump. Here's the things to memorize. I'm just going to write them here. You write them down in your notes. I wouldn't write them on the pink packet. I put them in your notes. You want to memorize that holes, and I'll just abbreviate so we catch up. You want to memorize that holes and vertical asymptotes only occur in rational functions. That's extremely helpful because that means you'll encounter problems where you don't need to worry about holes or vertical asymptotes. Rational just means the function is a ratio. It's a formula that has a top and a bottom. Okay? This is a rational function. So it could have a hole and or a vertical asymptote. Okay? If there's no bottom, you can't have a hole or a vertical asymptote. That's all that we mean by rational function. Follow-up questions on that. Okay, next thing to memorize. Hole, I should say, holes occur at values of x which cause the y value, remember a function is just an x and y pair list, so holes occur at values of x which cause the y value to become 0 divided by 0. So a hole occurs when you get a y value, like a value of x, which causes the y to become 0 divided by 0. Do an example here in a second. Pretty good with that. Okay, next thing. Number 3, vertical asymptote occurs at values of x, which cause the y value to become some number divided by 0. N represents any number, 5, 10, -6, whatever. So a whole is when you get a y coordinate that's 0 divided by 0. A vertical asymptote is when you get a y coordinate that's some number divided by 0. Question? Awesome. Okay, let's turn to problem 17 in the pink. This will help illustrate what we're talking about. Get a couple more things memorized and we're done. Okay, first thing on problems 1 through 17, it's just like limits. If you can factor, please factor. Okay? Factor and divide if you can, always. The one difference is before you divide, you need to kind of look at the function. So 17, this is a piecewise function, but I noticed that the first part of the piecewise is rational. And so I factor it. So write this down in your notes. X minus 2. The bottom factors into x minus 2 multiplied by x plus 1.
Wait, how did you get the number?
To factor it?
Yeah.
So the way I factor it is I say, let's see, x times x would be x squared.
Yeah.
What multiplies to make 2? Only one thing, 2 and 1.
Okay. How did you choose that the formula though? Yeah.
Oh, you're okay. So I get the 2 and 1. You okay with that?
Yeah.
Now all I have to figure out are the plus and the minus. So I just multiply it out to see what happens. So I say x times x is x squared. X times 1 is 1x. That's negative 2x. That would be negative 2. That's what I want because these two add to make negative x.
Yeah.
That's how I figure the values.
So, never mind. Wait, I got
You're
it.
okay. No worries. We'll talk in a minute first. You good here? Okay. Notice something. You have a factor in the numerator which matches a factor in the denominator. Okay. Those matching factors are going to cause a whole. Because if you choose x to equal 2, I just say it, what will the numerator become? 0. This portion of the denominator will become 3. Who cares? This portion will become 0. That 0 multiplied by 3 is 0. So I know there's a whole at x equal, wrong button. There's a whole at x equal 2. We're almost there. Questions? Don't go on the bell. We just need a few extra seconds. Right?
I just don't quite understand how you got the x equals the negative.
No worries. So are you okay that what causes the whole is like some unknown value of x, which results in the formula, like how we get the y coordinate, Ryan, being 0 divided by 0. Does that feel good?
Yeah.
Awesome. Okay, once you get the formula factored, okay, everybody, you can't do this without factoring. It's like near impossible. But once we're factored, I just kind of look at the factors. If I see matching factors, I'm like, oh, I got it. If I plug in a 2, it's going to be 0 over 0. Will that help?
Yeah, that's
good. Okay, vertical asymptote, easier. All you're looking for is a factor of the denominator, which can cause the denominator to become 0. So you don't use this one because that caused the whole. It's this one. So there's a vertical asymptote at x equal negative 1. Questions? Please.
So why don't, so you can't use whatever causes the whole, you have to use the other types of it?
Right. Keep the whole and the vertical asymptote separate. Look for the whole first. So it doesn't cause both. So these matching factors cause the whole. So I always look for those first pairs. The remaining factor causes the vertical asymptote.
Okay.
Last thing, jump. It's going to take just an extra minute to stay. Okay. Memorize, please. Write it down. Jumps only occur in piecewise functions. The jumps are actually the easiest thing to find. Jumps only occur in piecewise functions. So if it's not a piecewise function, don't look for a jump. Jumps only occur in piecewise functions. Next thing, jumps are easy to find because they only occur when you transition from one part of the piecewise to another. So look up here, like mine's on the board, so I'm going to take a few more seconds. Okay, you can plug in a whole bunch of different x values into this formula. In fact, any value that's less than or equal to 3. But if you're going in order, the last x you would plug in would be exactly 3. Feel good about that. So I write that down. If I plug in 3, look here. Okay, these factors still match. They divide to make 1. 3 plus 1 is 4.
Can we please have Owen Reynolds, Ellie Johnson, Hannah Baker, Ryan
Plug in 3, the y
Russell, Isaac
value is
Marion,
1, 4.
Sam Sullivan, Kate
The very
Baker,
next
and
3
Katana
that you
Council
plug
come to the
in
main
is
office,
3
please.
plus. Just a little more. But the 3 plus doesn't get plugged into this formula anymore. Okay, when you change from one formula to another, that's when you can possibly have a jump. So I have to plug the 3 plus into this one. Now, if I plug it in and get 1/4, or really close to 1/4, no jump. Okay, see what I'm saying? It's when the y coordinate changes suddenly. The x isn't changing hardly at all. If the y coordinate changes, that's a jump. So in this case, 3 plus squared is pretty close to 9. 9 minus 9 is not exactly 0, but pretty close. Okay, that's a jump. So there's a jump at x equals 3. I'll let you check the other one. There's also the answers in the back. When you go from this formula to this one, that's going to be at 4 versus 4 plus. You have to check for a jump there as well. Good work, Steve. Well done.
Okay.
Really well done.
So do 1 through 17.
1 through 17. Good work, you guys.
We only do those grouping 1 each time.
There's a, there's not like a question, just kind of review it. You're welcome. Good job.
Wait, what do we do with this white paper?
The white paper is just notes, just to help you if you need it.
Yo, I'm starting to do these like trainings that I did like last spring.
They're like all good.
Like that is destroyed.
Yeah.
My knee is like somewhere into it. Oh, my legs are just so knee to knee. Bad, we needed knee. That was so cute. At halftime, that was dying.
You got scared after?
And he looked serious and then he just
Okay, I can just. You still have that one.
certain halves of the field. So don't like get close to them. Stop. And then as soon as we get to the far end,
Why am I
just going off.
Perfect, and that's good.
So,
What is?
So you just talk to me.
I love
Like, I'm
factoring.
pretty, like,
I love
I'm not-
factoring.
I'm a
Factoring
stickler as far as I can
yeah.
just
Full of
but when you're not here, you just kind of talk to me.
I know, I think it from, so you just keep factoring and then those things last week, X minus 6.
I'm actually better if you just come talk to me and get back to me. You already know about the videos and stuff.
Yeah, I'll be watching it.
All right.
Like the big deal.
so pretty much like
Negative
solving
plus, just put factoring.
Oh, okay.
It's like the same, well, not exactly.
like the first couple of problems.
So that's where your hole is. This is what we were just talking about. There's a hole right there. So your hole. So when you plug in 4 right
You
here,
resemble, what you're noticing is the functions that ask you
Negative 4 plus 4 is 0.
Looks similar.
Negative 4 plus 4 is 0.
But it's
0
important
divided by
that
0
you
is
keep in your
1.5.
mind that it's
There's
separate
a whole
things.
right.
Finding a limit is different.
Well, because
than
0
figuring out whether
times
there's a whole
that.
or less.
We don't even go as a zero.
So you're just
No.
you can plug it into the whole equation and it'll be the same thing. Because if you just plug it into this part, you're gonna get that.
So
Yeah,
let's
no,
do number
that's
two.
why you have to keep this part. Because this is the whole. So, you technically, it plugs into the whole equation,